Today we're going to learn a statics problem, a three-sided triangle with angles. So let's take a look at what we got here. Okay, so we have a triangle with beams AB, AC, and BC with a force applied to it. So at B, horizontal force pushing in at B. So first thing we try to do is to visualize what's happening with the beams. BC is going to have to go into compression. So we'll take a look at these forces now. BC has to go into compression to push back at the force F. But by going into compression, it's being pulled away, and so the beams AB and AC have to go into tension to hold BC into place. So let's take a look at B. Again, we have the force pushing in on B, and the horizontal part of B, BCX, has to push back with an equal and opposite force. That's also going to produce at B, BCY, which means the beam BC is going to try to be pulled up by the force. Now, the forces that are happening at B are also happening down at C. So you can see BCX and BCY there. Think of it as the force is just being transferred to the beam, through the beam to the other point C. Those forces are equal, but if you look at it, you'll see that they're in opposite directions. So BCX is pushing to the left on B, but it's going to be pushing to the right on C. It's pulling up at B, but it's going to push down at C. So we have a couple things. The beam AB has to counter the tendency of the beam BC to go up, and the beam AC has to counter the tendency of the beam BC to go to the right. So AC will go into tension. That pulls on pin A, and then pin A has to go AX to the left, which will be equal and opposite. From the vertical, we see AB has to pull down on BCY, which means it pulls up on the pin A, and the ground force AY has to pull back down. Conversely, on the other side, since BCY is pushing down, C of Y has to push back up. So we get a visual. Also too, by looking, we can see some forces that are aligned with each other, so that means they're going to be equal. So if we look at the horizontal, we see AX is going to be equal to AC, which is equal to BCX, which is also equal to the force up there. In the vertical, we have A of Y is going to be equal to AB, which is going to be equal to BCY, and at point C, BCY equals C. Okay, so let's put some numbers and see what we got with this. We'll say our force, our external force equals 100. And since we already know what our sines and cosines are, we're going to replace BCX and BCY with the cosine and sine of 65. Y at B of X, why did we use the cosine? Because I needed the horizontal force. And in this sense, the cosine, or AC, the cosine of 65, the adjacent over the hypotenuse, the adjacent is the horizontal force. So that's why I use BC cosine. Likewise, the vertical part would be BC sine theta. So that's why I see BCY as BC sine theta. And I use the same numbers over at C. And so again, all of our things still apply. Okay, so AX equals AC, which now equals BC cosine 65. AY equals AB, which is BC sine 65. Okay, so let's see what we got. There's actually two ways to start this. You can either solve for a known force against a single beam, and in that case we would know we have a force of 100 pressing against BC, BC, and that would be the horizontal part I need, so it would be BC cosine 65. Or I could solve for the moments around A, meaning that at A the structure is trying to go clockwise and it's being pushed up counterclockwise by C of Y. So then I can say, well, the force times sine 65 equals C of y times cosine 65. Notice I'm using the sine and the cosine as a length. Since they're both a decimal value, the ratios are going to work out right. So I'm just going to go ahead and use those sines and cosines as lengths, as decimal values lengths. So 100 times 0.91 divided by 0.42 equals C of y. In both scenarios, we see that, I see that C of y is going to equal to 214.4. I do the math for each one, and I find out that BC equals 236.6. This is a good sanity check, because this said that whether I use the horizontal portion or the vertical portion, both answers gave me the same answer, which is 236.6. So I got a high degree of confidence that I'm doing the right thing. All right, so let's put these equations into a matrix so we can see what we're doing. We're basically looking at the methodology of how we're solving this. So I'm going to put this in a form of AB plus AC plus BC equals something. In the left side, I used my B of x equation, so I basically just said BC cosine 65 equals 100. In the right side, I used my C of y equation, BC sine 65 equals 214.4. Okay, great, got them there. All right, now that I know what BC is, I can use that to solve the other two beams. Since we mentioned before, BC sine 65 is aligned with AB, they're equal and opposite, so AB equals BC sine 65. I can take a look at this, and I'll put this in my next set of equations. Notice I can use it for both of them. Okay, so I can say AB times 1. My equation simply says AB equals BC sine 65. So when I put it in my matrix, I say AB times 1 equals BC minus sine 65. Okay, so AB minus BC sine 65 equals 0. They balance out. And I do that, I put that in for both of my equations. So I can now solve for I can now solve for AB. Okay, and then let's go back to our AC. I can see that BC cosine 65 is going to equal AC. Okay, and by the way, that's also going to equal A of x. So I can go ahead and put in my last equation, AC equals BC cosine 65. Or in my matrix form, I would say AC minus cosine 65 equals 0. And I find out that AB times cosine 65 equals 100, which is kind of what I thought. And if I look, I have a nice sanity check. My A of x, my ground force, is opposing the external force of 100 up there. So all my external forces going left are counted by my external forces going right. If we look at the vertical force ground forces, AY is 214.4 pushing down, C of y is 214.4 pushing up. So all of my forces equal out, everything looks correct, and we've just solved a three-sided triangle with angles, and it was easy. Thanks, bye.